All right, good morning from Chicago. This is Tim Stewart. I'm president at Visual Decisions, and we're here today to talk about reducing the cost of quality and escapes with predictive quality techniques. At Visual Decisions, we've been in the business of utilizing information from the shop floor to improve continuous improvement since about 2002. We help our customers combine the smart factory with the lean factory to drive improvements to cost, throughput, and quality. Our customers have seen dramatic improvements such as 30% increases in OEE, 50% scrap reductions, and much more. But just like wearing a Fitbit won't automatically make you thin, implementing technology for Industry 4.0 won't automatically make the business better. The culture of the organization and the business processes have to be adapted to take advantage of the new capabilities to drive real improvements. That's why we have a unique approach to work with our customers to adapt processes to take advantage of the new capabilities and help establish a true data-driven manufacturing culture. As a quick procedural note, if you have questions during the presentation, please enter them into the Q&A and I'll get to them at the end of the webinar. So the goal for today is to talk about predictive quality, what it is, why it's important, and then to go through some of our experiences implementing predictive quality with our customers and some of the lessons learned that we've gotten from there. I won't get very deep into the different predictive analytics themselves. So I'm not going to talk about the difference between a neural network and a SVM or random forest or anything like that. But I will talk about some of the things that we found in terms of how to identify the data that you should be mapping and how you go about that process and how you contextualize the data and so forth. So with that, if we look at what predictive quality is, fundamentally, it's the ability to identify when a defect is likely to occur prior to when that actually happens. And that's usually achieved through some level of process monitoring where you're collecting information from the different machines and so forth, statistical analysis and or machine learning. So why is predictive quality important? Well, first of all, it's just another tool that you have in your arsenal to reduce the total cost of quality. And when we look at how the cost of quality can be optimized, you have your cost of good quality, which is your prevention costs, and then you have your cost of bad quality, which is your failure costs. And obviously, if you want to get to 100% quality, excuse me, within your facility, you can not only work on getting good quality in the individual steps of the process and doing lots of testing within the process and so forth, but you can also just inspect the heck out of the parts in order to ensure that no bad parts actually leave the facility. And so those are the costs that we're talking about when we talk about prevention costs. With failure costs, that is scrap and rework, the material losses, expediting fees to bring in new materials or to get late builds because of quality out to the customer in time, things like that. And so the optimal quality level is going to be where that total cost of quality is minimized, where you're balancing your failure costs and your prevention costs. What predictive quality is really going to help you with is reducing that cost of prevention. So if you can find quality problems earlier in the process, it costs less to fix them. If you can prevent, if you can stop a machine at a point where it's about to produce bad parts, then you don't have to scrap that material. You don't have those costs associated with, you don't have rework costs for those parts and so forth. You don't have costs of shipping those bad parts out to your customer, having your customer charge you back for those and so forth. And so the further something gets along the line, the higher the cost is for that individual failure. And by implementing predictive quality systems, we're able to minimize the cost of each individual event. And so, it really does help with minimizing your overall cost of quality. And when we look at that overall cost of quality, we can split that, as I said, into kind of an internal cost of quality and then an external cost of quality, where you have your cost of good quality and bad quality within your internal cost of quality, and then you have escapes and warranty claims as part of your external cost of quality. And as bad as your internal cost of quality is, having those things become escapes and warranty issues and so forth are much, much more expensive for the business. Not only in those direct costs, but the indirect costs of marketplace reputation and everything else. So there's really a lot of incentive to improve your quality as much as you possibly can within your environment, while looking at how you do balance the cost of good quality and cost of bad quality. So when we look at quality and what causes quality issues in the first place, we have, fundamentally, quality issues are the result of variation in the process in every case. Whether that source of variation is from, man, where someone's not running the process correctly, or, just making accidents and so forth. The machine might have underlying variation within it. In fact, I guarantee it has underlying variation within it. The method, whether it's set up improperly or something along those lines. There could be fluctuations in the material itself, how you're measuring things, the environment, environmental conditions, and so forth. All of those can lead to defects in the product. And when we look at predictive techniques and so forth, at least for the current state of the art, they focus primarily on the machine, because that's where we can gather the detailed information that will help us with these predictive capabilities. So before I get too deep into the predictive aspects of it, I want to talk about a few of the basics first, because in every situation, we shouldn't, if we look at a crawl, walk, run process, we shouldn't just line the babies up in the starting gates and have them try to sprint down and beat the world-class sprinters. So what are the things that we need to put in place first before we can really get to the predictive side of things? And so when we're looking at the information that we need to be collecting in the first place, you can implement a variety of different systems for collecting data from the process itself. And there are dedicated OEE systems that can collect information at the machine level. There are SCADA systems. There are MES systems that contain some of these different applications within them. What we have been using most frequently at Visual Decisions recently are IIoT systems, or Internet of Things systems, that allow us to connect to just about anything on the shop floor, and then basically create whatever workflow we want with that information once we obtain it. And so by doing this, we can look across different processes. Some of the specialized systems that I talked about only look at one machine at a time and can't contextualize that information across different processes. Where that becomes a problem is if you are looking at a machine and you're trying to predict quality at a machine, but you don't test the material until several steps downstream. Then if your system is only looking at one process at a time, you just don't have that output variable of the product quality that you can actually tie into your analysis capabilities. So then if you look at some of the additional things you can do with that, you can contextualize that information in a lot of different ways. And I'll talk about that more in detail on a couple slides from now. Another thing that's very key in this whole process is tying this information into your Kaizen process. And so there are numerous capabilities within Lean and Six Sigma to really improve the quality of the process as it stands today without even getting to predictive quality. So as you're working your way towards predictive quality, how do you take this information that you're collecting from the IoT system or other systems and now work that into your quality process? How do you actually embed that into your Kaizen process, doing your root cause analysis and everything else? And I've done detailed presentations on embedding this into a Kaizen process, root cause analysis, and so forth. And if you're curious about this, I recommend that you go to the website at visualdecisions.com, go to the different presentations, and all of that information is there. In addition, there are more advanced capabilities within the Lean Six Sigma toolkit, such as FMEAs, that allow you to do a deeper process analysis and start to tie that information using these IoT systems into the information that you're collecting from the machine, looking at the specific failure modes, and now tying that into the data that you're collecting from the machine so that you can increase your probability of detection. You can decrease the occurrence, and you can also decrease the severity. And this starts to actually now tie into what we want to do from a predictive point of view. Because as we're looking at a particular process and thinking through, what are the failures that we're actually trying to predict? Running through an FMEA first allows you to really do the analysis that says, for this particular failure mode that is, we believe occurs, in this process, here are the different root causes for that. And, here's how we believe we can detect what's going on within each one of those failure modes, or how we can detect those failure modes. And so by doing this FMEA process up front, it really helps with the implementation of some of these algorithms to correctly model the process so that you're going to collect the right information to be able to then train the model to detect the failures or predict the failures. So that takes us to the predictive analysis itself. And when we look at the predictive analytics workflow, as I was talking about with the FMEA, finding the right inputs to the model can be a challenge. And that's both on the actual input to the process side, the process variables themselves, as well as what are the actual outputs of the physical process that we're going to try to predict using the model. And so if you look at the different failure modes, what are the measurements that you're going to be looking at in the end product that will actually detect that particular type of failure? And then for the different root causes, what are the different signals that we should be looking for that are going to correlate to that failure mode so that we can start to look at those different signals so that we can then predict when a failure is going to occur. And so as we go about all of this, we're going to start by accessing and exploring the different data, whether that's coming directly from the machine sensors, or if we put that information into a database first and then do the analysis and so forth. There's usually a process or a pre-process of working with the data because you'll have missing data, you'll have bad sensors, you'll have different things where you're trying to contextualize the information so that you can do that feature extraction of what materials being run through the process, what part ID is it, who's running the process that day, environmental conditions, and so forth, that all may have an impact on your predictive model. So then taking all of those things into account, you're going to start developing those predictive models, and you're going to try a number of different algorithms to see which one fits the data the best, is the most predictive. And typically, there are a couple of different ways to go about the predictive analysis that's a little bit beyond the scope of this particular webinar, but You have models that you train offline, essentially, where you have a historical data set, and I'm going to divide that data set up into 70% that I use for training my model, and then I test the predictive capabilities of that model against the remaining 30% of the data. And by doing that with multiple different algorithms and so forth, I can see which one of those holds the most predictive power for my data. The other type of algorithm that can be put in place is one that learns continuously as you get new data. And there are strengths and weaknesses of both approaches in terms of flexibility, speed, predictive power, and so forth. But all of those things exist, and various solutions help you through that process these days of selecting your model and doing the training. And then finally, the other kind of last step is to integrate with systems. And this talks about systems themselves, but you should also think about the human systems and the processes that you have in place within your business. As I say with the Fitbit, the Fitbit itself doesn't cause you to lose weight. You actually have to, change your behaviors, and that's what's going to, drive the benefits for you. Just because I'm predicting a failure doesn't mean that an action is automatically going to be taken to prevent that. So once I predict that the failure is going to take place with different degrees of confidence and so forth, somebody still needs to, take action on that and either stop the process, make adjustments, etc. So I've referenced this a couple of different times, but finding the signal in the noise can be very difficult. And so a lot of predictive systems or predictive system implementations today fail because the data is not properly contextualized. And I'll actually give an easier example of this from predictive maintenance. When we look at predicting failures on a machine, what is very often the case with some of the specialized systems today is that they'll just look at the signals coming from the machine itself and try to predict failures based upon that. But what they're doing is they're using as an output anytime the machine goes down. And the machine can go down for a number of different reasons. And a lot of those have nothing to do with the actual machine having an issue. So you'll get an e-stop. That could be the operator going to lunch or attending a meeting. It could be that he ran out of parts. There could be a safety issue, somebody walking through the process or walking through the environment and so forth. And so there are a million different reasons why you could have an e-stop on the shop floor. But if you don't separate those e-stops out from the rest of the data and you still run your predictive algorithm, then that's going to bias your algorithm because you're looking at what was happening in the machine when those failures occurred as well, instead of just isolating it down to the particular types of failures that you're looking for. And it's the same thing with quality. I have to have clean signals on what are the actual failures, what type of failure was it, was it that my OD was too big, my OD was too small, was I above tolerance, below tolerance, was it scratches, was it some other type of defect. So that type of signal coming from the output of the process is very important. But then I also have to have clarity on some of the inputs and the process variables themselves, as well as environmental variables such as who was running it, because that can make a huge difference in terms of my predictive power. One person may run the process one way, another person may run it a different way. Hopefully you have standard work in place, but it can still make a big difference when you have an experienced operator versus an inexperienced operator, even if they're trying to adhere to standard work. And so those types of external factors are very important to consider and pull into the model to really improve the predictive power of that algorithm. And so, as I'm trying to find the signal in the noise here, there are ways that you can pre-process that information, and the more context that you have, the better off you are for creating a clean data set to actually predict your different failure modes to occur. And just some ideas on how you can contextualize that information with different factors here. I won't walk through the entire circle or ellipse there, but those are different factors that you may want to consider for contextualizing the data so that you can go through and do that predictive techniques. One question that I get asked is why predictive maintenance gets so much more attention than predictive quality. So when you look at different companies, just an example, partner of mine is PTC with their ThingWorks IoT platform, and they have machine learning built into that. And when you listen to their presentations and so forth, they talk a lot about predictive maintenance, but they don't talk a whole lot about predictive quality. And part of the reason for that is that predictive quality is just harder. With predictive maintenance, you're really just looking at the machine itself, and you're, there's many fewer external factors that are going to have an impact on the performance of that machine, whether it's running or not running, and so forth. And furthermore, most all of the information that you need to run predictive predictive analytics on that machine are right there with the machine itself. With predictive quality, not only do you have many more potential causes with man and method and material and so forth, but you also have the fact that some of the variables that you have to look at may not happen right at the machine itself. And so you might have a process where you are milling a part, and then it goes through several more operations downstream before it actually gets measured. And because of that gap in time, it can be difficult, especially if you don't have serialized products, to correlate when that failure occurs to when that was actually on the machine. So I can clearly look and see what signals I should be looking at on the machine that will tell me, when that product is likely to fail. And so there are complicating factors with predictive quality that make it a lot more difficult in certain manufacturing circumstances than others. And that's something where, if you're interested, give us a call. We can certainly walk through that process with you and find out, or give you, an estimate of how hard it's going to be within your environment to be able to do this. So walking through a particular customer example, they have a process where they're doing grinding, and they're grinding a particular product. And for that product, they have two issues. One is if they leave the wheels on too long, they're going to produce burnt ends on that surface that they're grinding. If they take the wheel off too soon, then they're spending way too much on the maintenance and new acquisition of those grinding wheels. And so the question for them is, how do they balance that so that they're not producing bad parts, but they're accurately saying when we can get more life out of that tool? And so the first step in that process is to connect up to the machines and get the information from the PLC and other sensors on that machine to get vibration data, noise data, power consumption, various time series data coming from the tags and so forth, so that you can have your basis for analysis. Then we're pulling that information into the ThingWorks system in that particular case. Again, there are multiple platforms out there that you can utilize. ThingWorks was the one that we utilized in this particular project. Oops, wrong way. The next step that we do is we run that through the ThingWorks applications for predictive maintenance, machine learning, or predictive analytics, machine learning, AI, etc. And what that helps us do is to analyze, the signals coming in. For instance, when we have this worn wheel, on the, I believe this was the power draw in this particular case, we can see the variability that we have in the power draw for a worn wheel. For when it actually fails, we can see what happens with the power draw in that particular case. And then when we have a new wheel, we start to see that it operates within a much tighter band as it's producing individual parts. And so because we have this kind of analytic, what we're able to do is to put bands around the variance on this and see where it is that we want to signal that we have a potential failure that might start occurring, where we might start producing bad parts. And by doing so and running that through the different algorithms and so forth, we're able to not only use that one signal, but then also potentially pull in vibration data, noise data, and so forth to combine those and improve the predictive power that we have within the algorithm. Once all of that is in place, then we can start to present those results on a computer, on a phone, through augmented reality interfaces and so forth. But the idea is that we need to give that information to the right people at the right time in the right way so that they can then take action on that information to either replace the wheel or look deeper into the process to see whether a change is required and so forth. So just a few quick lessons learned about all of this. One question that I get asked is, what is the best time to gather data? And it's a little bit like the question of when is the best time to plant a tree. As the saying goes, the best time to plant a tree is 20 years ago so that you'll already have the shade coming from it. The next best time is right now, so that you'll start to grow that tree and have that available to you later on. It's the same thing with data. The best time to start collecting data is 2 years ago, so that I have 2 years of history on that process to start training my algorithm and so forth. The next best time is right now. If you want to know what data should be gathered, first of all, if data collection and storage were free, I would say do everything. And just collect everything, store everything, and then you have everything that you need to run the predictive analytics. Since it isn't free, the next question is, where should it be gathered? And first of all, if you have a process that's out of control, if you're doing SPC throughout your facilities, as an example, and you know where you have process control issues, obviously start there. The next thing would be if you have processes that are deemed to be critical, you've done process FMEA and so forth, and you believe that you have a high RPN in particular areas and so forth. Again, those would be something that would provide a good payback for spending on putting those predictive capabilities in place. So once you've identified where, use one of the frameworks to do the analysis to figure out what data you should be collecting. And as I mentioned, an FMEA is a good one to be able to say, for the different causals, what are the different ways that you might be able to predict that? What are the different things that might be correlated to that particular failure mode? And then once you have that data collection plan, start to put it in place. But then it's also very critical to put control plans in place to monitor that information, because you don't want to have the situation of garbage in, garbage out. A lot of these models are black boxes. For instance, neural network, it takes its inputs and it gives its outputs, and you don't really understand why it's making that prediction. You just know what prediction it's making. And so if you put garbage into a neural network, you will get garbage out. And furthermore, if you put that into the training portion of it, you're going to corrupt your predictive capabilities. And so it's very, very critical that you're cleaning the information and keeping that clean as you're passing it through the algorithm. So putting that control plan in place to sense, what are the characteristics of the data that you should be collecting? Is it within those ranges? Are you seeing extraneous data and so forth? Are you getting gaps in your data? And how should you handle those and so forth? And then, what are the other factors that might be influencing that? And, making sure that you have control plans in place for those as well. So some closing thoughts here. Predictive capabilities are a critical addition to the toolkit and can really, really help significantly impact quality, particularly in certain environments where you have the ability to get those clear signals. IIoT systems can really provide significant context of not only what's happening, at the machine level and so forth, but also some of the different environmental factors and upstream and downstream information can be, gathered together so that you can do a better predictive job and better contextualize that information. And then in order for this to really be effective in the long run, the tools have to become part of the standard work for really multiple organizations within the company. Quality should be involved in this process in order to, get things set up and analyzed correctly. Continuous improvement should be involved. Production obviously has to be involved. And so this really has to be embedded into the standard work for not just the operators, but for the organization as a whole. With that, thank you very much for your time today. If you have questions, please reach out to me, tim@visualdecisions.com, or my phone number is right there as well. Thank you very much, and I look forward. We do have a question in the Q&A. Have we analyzed IIoT data to analyze material flows? Absolutely. So there's a variety of different ways to analyze the material flows using IIoT data. One way is if you have, for instance, a traveler that goes along with that and you're barcoding things, you can take that barcode and incorporate that into your IIoT data. You can also start to look at things like RFID tags that travel with the different materials, and being able to tie that RFID data directly into your IoT system so that you can track those material flows. All right. There aren't any other questions in the Q&A, so thank you very much for your time today, and I will follow up with you all here in the coming week. Thank you. Bye.